Now that we have the analytic solution for our second example, we can do basically the same thing we did for the first example when we put it into MATLAB. So let me bring up MATLAB again, and I'm going to take what we had for our first example, and I'll just start by copying it. There's no reason to do everything over again. But we do have to modify a couple of things here. So first, here the period was different. The period was only 2 seconds in this case. So that's going to also change that frequency. I'll start again with only using 1,000 points in time, and I'll do it for 5 periods again like we did in the last example. And here the definition for x is different now because we have this piecewise function that we have to employ. But we can still use this modulo again. We just have to be a little bit careful with it. So it has 2 regions when t is 0 to 0.5 and when t is 0.5 to 2 seconds. So we can actually define those 2 regions. So I can say 0 times mod of little t big T. So if I only do this and have that end, let's see what happens if I plot that. Now x only has values of 0. So it's not always 0 though, it's only 0 as long as this value is less than 0.5. And then it's going to be 2 when that value is greater than 0.5. So we can see what that looks like. Just do a quick check here. So if we plot that, now we have this function out again. So again, we use mod, but now for the piecewise, we can define it within regions here using this logic statement of less than 0.5 or greater than 0.5. And if it had more than only 2 pieces to it, we can keep extending using these logical statements, but we'll save that for future examples here. This one works. We do get our original function back. Right, now we can continue on. This one I'll go up to 50 for my truncation here, and I have to put in this different piece since the inside of my summation is obviously different than it was in the last one. So inside I have 1 over n times the sine of pi n over 2 times the cosine of pi n times t plus 1 over n times cosine pi n over t minus 1 times the sine of pi times n times t. Right, so that is the stuff inside this summation. So like we saw in the last one, we're going to use this cum sum down here, but the outside is different. This is now 3 over 2, and this is going to be multiplied by 2 over pi on the outside. But most of it we can recycle the same way we did before. Looks like I have one too many parentheses here. Let me rerun this. It looks like I had a typo. This is n pi over 2, not over t. All right, so now it's working here. And just for the sake of this one, let me look at if I only use one partial sum, I'll go all the way up to 15, and I'll go up to 30, just by modifying these. So 1, 15, and 30 for my comparison here. Right, so if I look at this plot, let me move my legend here. Again, my one term is just this simple sinusoidal type of wave I have. My original function is now in black. And I see as I go up to 15 terms, as I go up to 30 terms, my approximation is getting better and better, at least on these straight parts of the function here. Now, just like in the last function where I have these discontinuities here, I'm getting this Gibbs phenomenon where it's overshooting at this discontinuity, it overshoots down here, and then kind of settles into basically the right answer. But every time it hits that discontinuity, it gets a little bit off. But let me look at the error that I have here. I'm going to calculate exactly the same way I did before. Everything about it here can also be preserved. So let me run just this error section. And we see here that, again, the more terms we add, the relative error at least is going down. This was using 1,000 time steps. So it goes up here around 18.5. And we're going to see the same thing happen as I put in more time steps and rerun this. Relatively, that value of error gets higher as I put in more values. Or absolutely it gets higher, but relatively this relationship basically stays the same. If I'm using 10 terms, my error is going to be a little less than half as much as if I only used one. And then that reduction in error starts to go down the more terms I add.